Votre courrier m'a intrigué. La clé de FortGen, c'est ainsi que vous vous décriviez, si les souvenirs sont exacts.
Hello, everybody. Sorry for this delay. Today, our speaker is Professor Christine Frecker from National Institute of Research in Computer Science and Control, France. The skills of Professor Frecker are computer networks, computer science, algorithms, network analysis, sampling, models, traffic, server, systems, and other. Today, the talk of our speakers is entitled Large-Scale Analysis for Closed Stochastic Networks with Finite Capacity Nodes and the Reservation. Thank you again, Professor, for accepting our invitation, and please, you can start.
Thank you, everybody. I'm sorry for the delay. Thank you, Rafik, for the invitation and for the introduction. I'm not a professor, but just I have a research position, but I will do my best to explain you this work. The title of my talk is Large-Scale Analysis of Stochastic Networks with Reservation. It's a joint work with my student, former student Cédric Bourdet, during his internship at INRIA. And then I continue the work with Anen Mohabet from Université of Paris-Nanterre. I will speak about the motivation, then present a simplified model with reservation, and then related work for a simpler model. And for this model, we will have two parts. The first is to the analysis of a special case, and where we can explain performance analysis, and the second part will be for the general case. Yes, there is a real motivation for this work. It's this car and bike sharing system, which exists in the cities as a green mode of urban transportation. They are popular because they are ecological, and also it's good for the user who are not obliged to buy a car. We focus on electric car, as you saw in the photo, an Autolib car in Paris here, and because of electrical purpose, they are in station at this time. So here, just to explain you that this is this worked, and this is also big, with 4,000 of cars in 1,100 stations, and small station with capacity 4 to 7. And now the system is completely different. We will not talk about this. We will not talk about this. Thank you, Rafik. Next. And what is the problem? The problem for this system is this issue. There are stations without cars and without parking space, available parking space, when some user want a car or a parking space. And the aim of the work is to evaluate this unavailability probability in a simple model. And there are two ways to improve the system. First, sizing, which means evaluate the optimal fleet to minimize the proportion of problematic station. And the second one is some balancing the system with active redistribution. The operator put car in other station just to make that available for the users when there are nothing. And the natural balancing, which is to propose incentives to the user to choose a better station. So we will spend some time with the model. The idea is that it's a stochastic network with where the nodes are the stations and the customer the cars. And it is a closed one because there are a fixed number of cars. And why stochastic? You have randomness in reservation or interval trip times, and also the routes. The principle of the system is that users reserve the car, and both the car and the parking space in advance. For Autolib, it's 30 minutes for the car and 1 hour and a half for the parking space. And once the car and parking space is reserved, it disappears for the other users. It is blocked. And after a while, the users take the car for the trip, and then after the trip, return the car at the parking space, which is reserved. So there are no problem to park.
So we can use the car only for 30 minutes.
Yes. Sorry, Rafik.
We can use the car, we can rent the car only for 30 minutes. And for the parking...
No. Excuse me, it's not clear. It is the reservation is less, should be less than 30 minutes.
Okay.
The reservation time is less than 30 minutes. If you reserve the car and after 30 minutes, your reservation is finished.
Cancelled. Okay.
And for the parking space, it's a bit longer. Other questions? I will explain it with a picture. So the model, excuse Rafik, it is an animation. you will have work. I will introduce the notation. We have N station. N is the number of stations. M is the number of cars. It's fixed for the moment. And everything is homogeneous. We have capacity K for the station, and it's the same everywhere. In the station, you see that you have 4 objects, black cars, which are the car available. You hear, there is noise. Did you hear me?
Yes, there is an echo. There are other applications, application open.
You hear me? Ah.
Sorry, there is some problem. Okay, no.
For me, it's not a problem. Ah,
No, okay, okay, perfect.
thank you. So there is 4 objects in the station. The black cars are available cars. The blue cars are reserved cars. And the blue points are reserved parking space by somebody which has not already which has not taken the car. And the red point is a reserved parking space by somebody who is driving. Yes. So when a user arrives at rate lambda, next, he reserves both the car, which becomes blue, and some parking space, which appear in the station. Then, after a while, an exponential with parameter mu, it takes the car, and next, at this time, the parking space becomes red, and he took the car and drive during an exponential with parameter mu. Not so. Yes. Alors, voilà. Before model. Please, Rafik, 2 slides before. Yes, the user reserve, and after some reservation time, he takes the blue car, which is his reserved car. Next. Yes, and he takes the car and go to the reserved parking space, which becomes red. And after the trip, yes, the parking space, he parked the car, which becomes available again. You see that we make a differentiation of the parking space because there are the time they are reserved is the sum of 2 exponential, the reservation time at the beginning, and then the trip time. So there is 2, and despite this, next, this state process, which is this x of t, which is what you see, the state of the station, is not Markov. Why? Because of next, because of this double reservation. And when the car is taken, we have to know where is the parking space which correspond to this reservation. So this is the main problem, the main issue of the model. And so next, just a few words. This is a simplified model. We don't take into account different things, especially heterogeneity, space heterogeneity. Everything is at the same, the parameter doesn't depend on the station, etc. And we take exponential distribution and not general distribution. The time inhomogeneity is not taken into account, and we simplified the model. Maybe I don't precise that if the reservation is not possible, there is no car or no parking space at the station, target stations, the request is lost. Yes, and no.
Sorry.
And yes, and both should be reserved in our model. In real system, you can reserve or not reserve. You can reserve just the car or just the parking space, both of them, and do not reserve at all. Yes, you can do all this, but we simplified the purpose. And instead of being rejected, if it is not possible, you can look for make another attempt. Yes, this is variant. And for redistribution, it is not taken into account. So related work, if without reservation, the model is simpler. Our state process has just one component, which is the number of bikes here. It's like bike sharing. You can not reserve the bike. It's and VIN of t is the number of bike at station I at time t. And for this, for this model, two approaches are possible, because we know the invariant measure for fixed n. It is I write that this is some product form, but of course the number of bikes at every station is not the different stations are not independent, because this is conditioned by the fact that the number of bikes is fixed. Yes, but we know the invariant measure for fixed n. Even if the capacity is finite, with finite capacity, is the standard result. It's a known result, which is called the blocking routing policy in Jackson network. So with infinite capacity, it has been this convergence. We can take the limit for n large of this invariant measure. For infinite capacity, it has been studied by Guy Fayol and Jean-Marc Lasgout, then Malishev Yakovlev, and then Georges and Xia in some different number of stations is fixed, and number of bikes tend to infinity with a different approach. And for finite capacity, it's no.
Sorry.
Please. I have to spend some time on this slide. I have 1 hour, Rafik, or
45 minutes, please.
45, yes.
Yes.
So never mind. I will spend sometimes on this slide because it's important. So finite capacity, it's a work I've done with Daniel Tibi. We know that the invariant measure for a finite number of stations, when the number of stations gets large, converge to independent variables which are distributed like as truncated geometric. And the parameter of the geometric is a function of the different parameter of the system with explicit, with one parameter rho, which is a multiplicative factor, which is given by some fixed point equation, which means that the total number m of cars is the total number of bikes, is the total number of bikes in the station, the first term, and the second. Do you see my arrow or not?
No.
No? Oh.
No.
And the second, yes, and the second term is the number of bikes outside the station. It is a more general model. I don't want to comment this formula, but the principle is this one, and this is a more general model, completely heterogeneous. You can put roots and yes. And the idea is for Guy, the idea is it is a local limit theorem, which give us which allow to prove this. The second approach is not to take into account that we have an explicit invariant measure, which is very interesting when we have for variance, when this explicit invariant measure for n fixed disappear, and we can divide the result on two parts. Theorem 1, which gives that when n tends to infinity, the process, the number of bikes in one station or in a fixed number of stations tends to some process which is like the number of q in the MM1 k q, but with the arrival rate which depends on t. This means that the number of bikes at the station is a time inhomogeneous Markov process. This is the what we called in the literature the Makin-Vlasov process. And the arrival rate, the service rate is the arrival rate of user at one station, lambda, and the arrival rate is mu, it's natural, it's mu, the trip time, the factor, yes, the trip rate or something like this, multiplied by the number of car per station outside the station, S, which is M divided by the limit of m divided by n, the number of cars per station, minus the mean number of cars at one station. So it's natural to have this. And the second theorem gives us the long time behavior of this queue, of this process, which is time inhomogeneous. So it is not true that it has an invariant distribution. It can have several, etc. And in this case, we have a unique invariant distribution, which is geometric with parameter rho, a truncated geometric, and rho is given by the same kind of a fixed point equation, which means the same thing. Yes, as before, the total number S, yes, I can rewrite S is equal to mu rho divided by lambda, which is the mean number of bikes outside the station, plus this mean of the geometric, which is the mean number of bikes per station. Next. So we will have the same kind of result for the first case. Rafik, I want to have the slide before. Yes, we will have the same kind of result. Our approach is the second approach, and we will have the convergence of process, which is called mean field convergence, and for the special case, the theorem 1 is very standard, and theorem 2 is much more difficult. And for the general case, theorem 1 is difficult because of this interaction and the fact that our process is not Markov. Thank you, Rafik. Next. So the special case, what I call simple reservation is, imagine that the user don't reserve the parking space and don't reserve the car and just reserve the parking space just when he takes the car. Yes. So the blue object disappear until the user takes the car. And we have just a state process with two components, the number of cars, available cars, V I n of t, and the number of reserved parking space by somebody driving, R I n of t. Of course, as far as we know, the invariant measure for fixed n is not computable, not explicit. Next. So we will take the mean field approach. What is the limit of the process when n tends to infinity? The number of cars also at the same rate, and the rate is converging that S, which is the limiting number of car per station, S as size, which is less than K for a real world purpose. So the idea is that for one station, the the interaction of other station is infinite, is small in one other n, and it's multiplied by the number of stations, so it's a mean of the interaction which is important. It is the overall idea. Next, and our theorem can be, our result can be explained as follows. In this asymptotic regime, one station, the overall process converge to a process which are whose distribution process is solution of an ODE, and this ODE can be written like this. Yes.
And what? Sorry, what is L? The function L.
L. Next, please. Next.
Okay. Okay.
All we have to explain is what is L. L, if y is fixed, Ly is the jump matrix for a tandem of Qs with overall capacity K. It's written in red, R plus V less or equal than to K. And this tandem of Q represent a station. Yes. And it's like for bike, we had an MM1KQ with an arrival rate which depends on T, and here it's the same. When a reservation is finished, it becomes an available car. When an available car is took, it is at rate lambda if there is it is possible to reserve a parking space in somewhere else, which is with probability 1 minus the probability y sub s that the station is is saturated. Yes. And one reservation appear in the same time at rate lambda if some car is available somewhere, which is 1 minus y 0.0. And the good news is that for a tandem of Qs, even with this capacity constraint, this is, there is an explicit invariant measure. Product form is just comment dire, a way to comment dire, it's a way to tell that this is a product of two parts conditioned by the fact that the number of qu'est-ce que je raconte? No, it is a product form in a special state space. Next. And for the proof of this convergence, the main ingredient is to change the process, to take another process, which is the empirical measure of the state process, which is the proportion of station at time t with k reserved parking space and L cars. And this process, which is much more simpler to deal with, because it's when n tends to infinity, the number of components doesn't go to infinity as the state process. So this is our process. It is Markov with this state space on probability measures and this constraint. This, yes. And we write the transition, we write the evolution equation in terms of Poisson process, arrival, etc. of the process, proof tightness, and with the evolution, with tightness, we have, it is, we can prove with the evolution equation that every limiting point is unique because it verifies some equation with as a unique solution. So this is the idea of the proof. Next. Thanks. And the second question, the second part of the analysis is theorem 2. It's the long time behavior. And the result is that this process has a unique invariant measure. We call it y bar, which can be, which is more or less explicit. Why it's the product form where this product form where the parameter you remember the first Q is an infinite server Q. We have a Poisson term, and the second Q is a one server Q. We have a geometric term, and the two parameters verify a fixed point equation, our solution of the fixed point equation. And we prove that there is a unique solution. And this is the main work where we have a lot, some work, because in dimension 1 for bike sharing, it's very simple, a monotonicity argument. And here we have in dimension 2, and it's much more difficult. And the idea is to mimic the dimension 1 case. Maybe I can explain here something. Yes. We look for the invariant measure. It's the solution of y bar, L of y bar equals to 0. And this looks like the invariant measure equation of a Markov process, but with the matrix jump, which depends on the invariant measure. So because when y is fixed, we know that we have this product measure, pi. We know that y bar is the at this form with parameter which solve something. This is the idea. And it is next, it is possible to express the parameter. It's just the arrival to service rate at the two Qs, the first two equation, and the third equation is the fact that the total number of cars is this, Why? Because if you take available cars plus reserved car, we have all reserved parking space. We have the total number of cars because a driving car corresponds to a reserved parking space in this simple case. So with some works, next, it is possible to prove, next, it is possible, before, it is possible to prove that there is just one solution. The idea is that take the third equation and some monotonicity argument is possible if you consider just one parameter and the other one is expressed as a monotonic form as a function of the other one, and it is given by a global inversion theorem. So everything is this is the main idea, a sketch of proof, next. And for this, the idea is that we can have performance asymptotics. So we are interested in the proportion of problematic station, which is more or less related by the number of unsatisfied users and etc. You can speaks about this, and this is given as a function, and we are interested to have this as a function of the fleet size parameter S, which is the number of cars per station. And for this, the trick is that this this curve is given by a parametric curve as a function of the parameter rho, because S is given as a function of rho by this fixed point equation, and the probabilistic the probability that yes, and this is given by definition, yes. So this is the trick, and here we have an implicit equation somewhere, but in the dimension 1 we have no explicit. You have everything is explicit, and it gives this. The curve compared the car system with the bike system. Bike is without reservation, and what we have plot for different level of traffic, lambda over mu 0.1, 1, and 10. And what we can see is that we can compare, we can see the impact of reservation. Alors, maybe for the red curve, the green curve, excuse me, the green one is for light traffic. And for light traffic, for light, the green, yes, for light is more or less the same. There is no reservation effect. And for the red one, we have poor performance, yes. And what we can next, it's the same curve, but we can comment, I can comment here the optimality, so the minimum. For bike, it's there is a miracle. For bike and for cars, the minimum is for rho or rho v equals to 1, which is very yes, which is very interesting for the explicit formula. For rho equals to 1, a geometric is a uniform. So the main result is that for bike, the minimum is when you have a number of cars per station, which is capacity divided by 2. It's the S star, the last line. Capacity divided by 2 plus some terms, lambda over mu for the bikes. And this means that it's minimum when we to have no the probability to find a bike or to find a parking space is minimum when the capacity the bike the station are filled at half k divided by 2 plus sometimes it depends on the load of the system. If the demand is high, lambda is high, the bike will be outside and we have to put more bike in the system. So with this, I think that it's clear. It's more clear, this expression. And the next, this slide, just to see that for the car, we can show that there is an extremum for rho equals to 1, but we cannot prove that it is unique. So there is a lot of things which are not so simple to prove. Next. But we can do asymptotics for this car sharing, and we have this result. For light traffic, you see that this is not so different. And next, slide is, and the slide before. Thank you. And for heavy traffic in red, it's a joke. You see the penalty, yes. The proportion of problematic station is 1 minus something, and yes. So we can have explicit. Next, maybe I have 5 minutes.
Yes, please.
Yes, voilà. In 5 minutes, I want to explain you the double reservation, the case our state process is not Markov. Next. But we have a Markov process somewhere. You have to take some process in N2, which is xi of sub ij, which is the number of car reserved at I with the parking space reserved at j. And we have also the parking space reserved by the at j by the driving users and the available cars. And everything is put in this process, and we have a Markov process. We can do next. And our process, the state process of one station, of the station, is this that I have that you know for the beginning, the number of reserved parking space by the non-driving users in blue, the number of reserved cars by in blue at V in blue, the number of in red the number of reserved parking space by driving user and they available. And next, this is a function of our process. The formula are here, the relation are here, but this Z of t is not Markov because when we focus in one station, we take this interaction. But the evolution equation of Z can be written as a from the evolution equation for X. And of course, because of non-Markovian character, we have some, at some place, we have X which remains. Next. So the question is the following: despite non-Markov, is there a mean field convergence for Zn of t, which means that is there a autonomous process Z of t which exists? And the answer is yes, because the main idea is that mean field eliminates this interaction. And for maybe you know, otherwise have a look. There is some example in the literature, very well-known example. It's the Graham and Miller work on the loss network with alternate routing, which is the model by Gibbons, Hunt, and Kelly, which this B-stability, which is some alternative routing. When a link is full, you take an alternative point, and we have these two links, which is who are in relation or related because of the 2 points. I have no picture for this. And another model which is with this kind of strong interaction like ours. Next. And the result can be expressed as follows. We have this Z bar of t, which is a time inhomogeneous Markov process, which can be described as follows by some Markov process, but yes, with a generator next. And this matrix jump, this is a jump matrix of a tandem of 4 Qs, which can be understood as previously. And the point is that we have an invariant measure for this. The vertical Qs are infinite Qs. The horizontal Q is a one server Q. Next. And we can deal with the second question, which is the long time behavior. And here there is a problem. Our theorem is not so, it's a weak theorem for the reservation enough small, the reservation time enough small, there is a unique equilibrium point. The problem is that it's very simple to have to restrict to 2 parameters, rho r and rho v, but this system, it's very difficult to prove that there is a unique solution in general for new general. because of the second equation, which is the mean just for 3 Qs instead of the whole system. Next. So the conclusion is that we have a framework to obtain the limiting stationary behavior for these large systems. And here we have a case with non-Markov process, which means that strong interaction disappeared at the limit. And we have results for the equilibrium point in dimension 2 and 4, which is not so simple. Thank you for your attention.
Thank you for your Dr. Christine Frecker. Thank you for this talk. Are there some questions, please?
Bonjour, Christine. I have a small remark. It reminds me also of polling systems in some sense. I remember that it was around 99. I made with a colleague of mine, with Frank Delcoine, we made the analysis of polling systems with in thermodynamical limit, and we got also as fixed point tandem queues like you got. It's there is a kind of similarity, which is assumptions were maybe I don't remember the details, but assumptions were simply classical polling systems.
Yes, because you are in dimension 2. You have some processing.
The final equilibrium point was given in terms of 6-point equations for tandem queues.
D'accord.
And one of them, as far as I remember, one of them was an infinity, infinity Q.
D'accord. Thank you.
But it's normal because reservations and things like this, it's at a flavor of also of polling systems. It's all very nice. Thank you.
Thank you for your Guy. Are there other questions? I have a question, Christine, maybe a general question. Your model of bikes and cars and stations cannot be modeled by urns. We have a system of urns which interact together. Okay, you can think about when you take a car, you take an urn, a ball from an urn, and you put it in another urn with some model. Is this a right modelization of your problem? In other words, can I modulate your problem as a problem of interacting urns?
We can.
Of course. The exponential lifetime here is the time when we decide to draw a ball from some urn.
Yes. You have in this model can be you can have different way to formulate the model. You can take queuing. You see it as a queuing network, as a particle system, which is very close for Yoon model. Yes, you can formulate this. I don't see the problem. After, what does it gives as a
okay
new result? I don't know.
Okay, okay, thank you. And here, when you, as you, when in this theorem with distribution yt, you mean that yt is the probability density function of z bar t?
Density, the measure.
What do you mean by with distribution yt? Yt is the density function, is the probability density function.
The measure at time t, yes, the probability at time t of the process.
Okay, okay, okay. Just for our public, please, can you give a quick definition of MM1Q? Just a quick definition, please.
I'm sorry for who doesn't know. MM1 and MM infinity are birth and death process on N. MM1 with the birth rate lambda, and if the birth rate is the arrival rate and the death rate is the service rate. For MM1, it's lambda and mu, and for the MM infinite Q, the birth rate is lambda and the death rate is mu x, the number of customers.
Okay.
Yes.
Okay. Capital K is the station saturation.
Capital?
Yes? Capital K
is the capacity.
The capacity of any station. Okay?
No, of the tandem.
Okay, and what about the capacity of any station? Of a given station.
A station in the model, and here I talk about a jump matrix for a tandem of Q. It's an open system of two Qs, and I took K as the overall capacity of the tandem of these two Qs.
Okay.
And it's the same. Yes, it's the station capacity.
Okay. Okay. And there are no conditions about the cars are all independent, and the station are also. That's mean when we take a car from station I, we have no restriction to put it in another on any other given station.
In our model. In our model?
Yes, yes, please.
In our model, because the capacity of the station is finite, if the station is saturated, you cannot reserve a parking space.
Okay,
so
the only restriction. Okay.
Yes, is lost.
Okay, okay. Are there other questions, please? If not, we have to thank again our speaker, Dr. Christine Frecker. Thank you for this nice talk, and see you next week with our speaker, Hélène Guérin. Next week. Bye.
Okay, bye. Bye.
Merci. Tu arrêtes l'enregistrement, Nabil, please. Hein? Nabil? Ok, je vais l'arrêter. Pardon, Christine, j'arrive vers toi.
Il y a encore des participants.
Bon, au revoir, Christine.
Au revoir.
On discutera de tout ça un jour.
Oui, oui. Oui, oui.
Allez, au revoir.
Oui,
Bonne
Rafik.
journée. Bonne journée à tous.
Rafik, نسكر c'est bon. Ok, ok. Et qu'est-ce que tu
Non, non, attends, tu fermes pas, juste arrête l'enregistrement.